Now, we want to do some problems associated with entropy calculations, and we are going to start with PV to TS diagram. So, we have already calculated PV to TS diagram for Carnot cycle, right. Now, we are going to do it for some other cycles and associated problems. Let us say we are going to calculate for gasoline cycles first. So, in gasoline cycles, first step 1 to 2 is an adiabatic step. In an adiabatic step, what happens is that dq reversible is going to be 0. So, therefore, change in entropy is going to be 0. Now, 2 to 3 is an isochoric step. In an isochoric step, dq reversible we know is Cv dt. So, therefore, dq reversible by t is Cv dt by t, and therefore, ds is Cv dt by t, and S 23 is Cv ln t, and since we are going from T 2 to T 3, it should be T 3 by T 2. 3 to 4 is an adiabatic step again. So, del S will be 0, and 2 to 1 is an isochoric step. By the same logic, S 4 1 4 to 1 4 1 will become Cv ln T 1 by T 4. Now, what is the total change in entropy? Total change in the entropy in the whole cyclic process is sum of all these parts, which is 0 plus Cv ln T 3 by T 2 plus 0 plus Cv ln T 1 by T 4. Now, we have to invoke the relation between T 3 T 2 and T 1 T 4. So, for that we need to put combine the relation of in adiabatic step 1 and 2, in which we can write T 1 V 1 to the power gamma minus 1 is equal to T 2 V 2 to the power gamma minus 1. Why we can do that? Because 1 and 2 are connected by an adiabatic path, and all along the adiabatic path T 1 V 1 to the power gamma minus 1 is constant. So, therefore, we can do that. Similarly, 1 and 3 and 4 are also connected by an adiabatic path, and therefore, we can use 3 and 4 relation as T 4 V 4 to the power gamma minus 1 is T 3 V 3 to the power gamma minus 1. We have done that before also. Now, let us take the ratios of these two. So, T 1 by T 4, since V 1 and V 4 is same, is T 2 by T 3, right. So, we have not done PV to TS diagram as of yet. What right now we are doing is just to show that the overall entropy is 0. First we will do that, and then we will talk about PV to TS diagram. Cv ln T 3 by T 2 plus T 1 by T 4 I will write T 2 by T 3. So, Cv ln T 2 by T 3, which means Cv ln T 3 by T 2 minus Cv ln T 3 by T 2, because for ln case we can write that ln x is minus ln of 1 by x, and they cancel, it gives 0. So, overall entropy in the cyclic process we are getting to be 0. Now, we are going to show that how the PV and TS diagram will look like. So, this is our PV diagram, where this is an isochoric step, this is an adiabatic step, and this is an isochoric step 1, 2, 3 and 4. Now, we have to understand one thing. So, when we write a TS diagram, then 1 to 2 is an adiabatic step, adiabatic compression. So, what happens in an adiabatic compression? Since dq reversible is 0, entropy change is 0, which we have calculated also between 1 and 2, right. However, it is an adiabatic compression. So, therefore, temperature increases. So, entropy does not change, but temperature increases. So, let us make it little bit shorter for a reason. So, now we have seen that del S 1 2 is equal to 0. Now, 2 to 3, how do we calculate that? So, we know that in 2 to 3 ds is Cv ln t, right, which means sorry, it is not that, ds is dq reversal by t, which is Cv dt by t, and S is Cv ln t, which means that S by Cv is ln t, and T is e to the power S by C V. So, the temperature increases exponentially with entropy by C V. It is almost like, let us say you can write y equal to e to the power x by a, that kind of function, or you can also write e to the power minus b x or plus b x. So, you see b is nothing but 1 by C V, b is 1 by C V. So, it increases exponentially. So, we have to draw the same way, okay. And then the 3 to 4 steps. So, this is 1, 2, this is 3. So, 3 to 4 step is of course entropy change is 0 and temperature is decreasing because it is an adiabatic compression. Okay. Now, 4 to 1 step. So, before we do 4 to 1 step, we want to do some calculations. So, I can always write 4 to 1 step, but there is an interesting fact about it, that whether this line will be bigger than this line or smaller than this line. Can you tell me? So, whether this changes. So, both 2 to 3 and 1 to 4 it will be exponential, right, but 3 and 4, the line 3 and 4 will be bigger or smaller. So, which means we have to see the temperature difference between 3, 4 and 1, 2 whether they are same or not. Can you identify from this Otto cycle or not? So, now the question is that whether the line 3, 4 will be bigger than 1, 2 or not. Okay. So, in order to do that, we have to find this relation of the temperatures between 1, 2, 3 and 4. So, in order to do that, let us write that our adiabatic expression, that T 1 V 1 to the power gamma minus 1 is T 2 V 2 to the power gamma minus 1, and T 4 V 4 to the power gamma minus 1 is T 3 V 3 to the power gamma minus 1. Taking the ratio, we get T 4 by T 1 is equal to T 3 by T 2. Now, from there we can rearrange that and write T 4 by T 3 is equal to T 1 by T 2. Let us subtract 1 from both, which is going to give us T 4 by T 3 minus 1 is equal to T 1 by T 2 minus 1, which is going to give us T 4 minus T 3 by T 3 is equal to T 1 minus T 2 by T 2, okay, which is going to give us T 4 minus T 3 by T 1 minus T 2 is equal to T 3 by T 2. Following that till now? Now, 4 is lower temperature than 3 and 1 is lower temperature than 2. So, we can rearrange it and write it as T 3 minus T 4 by T 2 minus T 1 is equal to T 3 by T 2, fine. Now, which is bigger, T 3 or T 2 temperature? So, this is greater than 1. So, if this is greater than 1, that means T 3 minus T 4 is greater than T 2 minus T 1. So, the temperature difference between 3 and 4 has to be larger than between 1 and 2. So, this line will be smaller and this line will be bigger. This is very important, you cannot do other way around, because typically people neglect the size of the lines. First of all, they neglect how you do the T s, it is has to be exponential, and secondly what they neglect is the size of the height of the bars of the adiabatic changes. If you do it correctly, that is what correctly, but this is still not quantitative, this is qualitatively correct, at least to show that the second one will be larger. Now, same for the gasoline, but here we are going to do it little bit faster. So, again from first step to the second step, it should be straight 1 to 2, and then 2 to 3 is again it will be exponential, but instead of e to the power s by C v, it will be t will be, the relation will be t is equal to e to the power s by C p. And then there will be a line and it will be like this 1 2. So, this is again straight down. Now, you have to figure out whether the 3 4. So, now is 3 minus 4 bigger than 2 minus 1 or not, that you have to figure out. That will be a tutorial problem, the same way we have done the Gaslin cycle. Okay. So, now let us do some other tutorial problems. So, show that Q reversible by T is independent of path by considering the following reversible changes in the state of an ideal gas. We already have done that for Gaslin cycle, that the reversible path is giving 0. Similarly, if you use the diesel cycle also you can get that, but this is a hypothetical cycle, and for this hypothetical cycle we can show that. So, let us say the first one is state 1 to state 2 and state. So, this is a TV diagram, this is not a PV diagram, not a TS diagram, it is a TV diagram. So, therefore, one has to be very careful while looking at it. So, 1 to 2 is an isothermal process, but there is a change in volume, which means an isothermal expansion process. So, the change in entropy of S12 is going to be let us say following reversible changes of in the state of an ideal gas. Let us take it to be n molecule ideal gas. So, Nr ln V2 by V1 in the first step, state 1 to state 3. Now, state 1 to state 3, this is although not mentioned, I think it is an adiabatic step. So, delta S 13, since it is an adiabatic step, of course, it will be 0. So, we have calculated this one, we have calculated this one. Now, 3 to 2. Will be the temperature is changing, but volume is not changing. So, it is a constant volume process, right. So, it is in a constant volume process, what we get Cv ln T2 by T1. So, it should be Cv ln T2 by T3. So, we got a cyclic process. So, if you want to calculate a cyclic process, however, you have to be careful. See, we can come. So, if I go from 1 to 2, that is same as going from 1 to 3 plus 3 to 2. So, we can write like S12 as delta S13 plus delta S32, or we can write that delta S13 plus delta S32 plus delta S21 is equal to 0. In that case, we are following the cycle in the same direction, that is very important, otherwise we will not going to get. So, here what we have to show is that this S12 which you have got here is same as sum of them together, which essentially is nothing but just T2 by T3, right. Now, how do we show that? So, in order to show that, okay, so one more step is remaining, calculation of entropy of 1 to 4. Now, 1 to 4 is what kind of this thing is a constant pressure one. So, delta S14 is Cp ln T4 by T1, and 4 to 2 temperature is changing, pressure is changing, volume is not. So, delta S42 is a constant volume process. So, Cv ln T2 by T4. Let us see, 4 is 4 to 2, 2 has a T1 temperature and starting with T3 temperature. Let us see if I have done correctly or not. So, S12 volume is changing V1 to V2, that is fine. S32 temperature is going from T2 to T1, T2 to T1. So, T1 by T2 it will be. Okay. Then 1 4 is T3 1 4 is the temperature is T3 by T1 and 4 2 is T1 by T3. So, now is fine because there are only 3 values. So, we should write that, but it is already written here. So, that is why I was not writing, but we can do that. So, this is because we can see that this is the same temperature. So, 1 and 2 will have the same temperature, which is T1. So, this temperature is T1 and for the volume 3, 2 and 4 all have same volume and this volume is V2 and this volume is V1. Okay. So, 3 will have a different temperature which is T3 and T4 has a different temperature. No, 4 has T3 temperature and the state 3 has temperature T2. Okay. So, now we will have to show that delta S12 is equal to delta S13 plus delta S32, right, which essentially means we have to show that NR ln V2 by V1 is CV ln T1 by T2. Now, again for that we are going to use the relation between this adiabatic process 1 and 3. So, 1 has T1 temperature and volume as V1, 3 has T2 temperature and volume as V2. Once we do that, then T1 by T2 becomes V2 by V1 to the power gamma minus 1. Take ln on both sides, giving us ln of V2 by V1 to the power gamma minus 1 or gamma minus 1 ln V2 by V1. And what is gamma minus 1? So, gamma is Cp by Cv. So, gamma minus 1 is Cp by Cv minus 1, which is Cp minus Cv by Cv, which is R by Cv. So, NR ln V2 by V1 is equal to, if I multiply by Cv on the left hand side, I have to multiply by Cv on the right hand side. So, which you are going to get, actually in this case of course, we can take mole number of moles to be 1. So, it will be just one value and Cv here we mean by Cv bar, otherwise it will be NCV bar and things like that, or you can write that NR. So, to make it simplified we can write as NR, like Cp minus Cv is NR. So, we will take 1 mole for this calculation. So, it is R ln V2 by V1 and what is the right hand side? Cv ln T1 by T2, which is giving us this one, which is giving us again R ln V2 by V1. So, right hand side R ln V2 by. So, that means these two values are equal. Okay. So, now we are going to erase this and show the other relation, that 1 4 and 4 2. So, the other relation says that delta S 1 4, we are going by this path, plus 4 2 is equal to delta S 1 2. So, what is delta S 1 4? Delta S 1 4 again is a process where temperature changes, pressure does not change and volume changes. So, Cp ln T3 by T1 delta S 1 4, right. 4 2 is a process where temperature changes, pressure changes, volume does not change. So, Cv ln 4 2. So, I have to say T1 by T3, okay. And delta S 1 2 is a process in which temperature is same, pressure and volume are changing, which is now nothing but an isothermal expansion process. So, it is R ln V2 by V1. Now, let us see left hand side. So, right hand side. So, this is our right hand side and left hand side is sum of these two. Let us sum both of them. So, C p ln T 3 by T 1 plus C v ln T 1 by T 3, that is what you have to do, which means we can invert it and write, or we can just sum it and say that this is nothing but C v ln T 3 by T 1 plus R ln T 3 by T 1, because we know C p is C v plus R, right, and we can invert this ln relation and write minus C v ln T 3 by T 1. So, this and this cancels each other, giving us only R ln T 3 by T 1. Okay. But we know that T 3 by T 1 has a relation with V 1 and V 2, right. 4 and 1 pressure is constant. So, 4 has P 1 V 2 by T 3 is equal to P 1 V 1 by T 1. Now, P 1 cancels, giving us T 3 by T 1 is equal to V 2 by V 1. So, this is nothing but R ln V 2 by V 1, which is our right hand side as well. So, which says that for this cycle the entropy for the whole cyclic path will be 0, because what we have done is that we have not followed a cycle, we have followed two paths from this point to this point. Again, that is the same thing that says that if I followed this cyclic path, then I will have to subtract this one, then it will be 0, right. Okay. So, we have done that. Now, let us calculate efficiency of an arbitrary cycle. So, this is showing some arbitrary cycle where 1 to 2 is a constant pressure process, 2 to 3 is constant volume process connecting by an arbitrary path 3 to 1 as an adiabatic process. Okay. So, while I am doing that, you should also try to do that. You can pause the video and try to solve the problem and then look at it how it is working. So, calculation of efficiency is pretty simple, because what all that you have to calculate, that heat in and heat out. So, we are going to calculate that heat input in first two steps 1 2 is a constant pressure process. So, it will be C p. So, when we calculate the heat changes, so C p it will be T 2 minus T 1, right. And then, and in this case we know that it is a constant pressure compression process. That means, in this process volume gets less. So, if the volume gets less, the temperature has to be lower, because pressure is same. Remember, it is an ideal gas. So, pressure is getting lower, volume pressure is same, volume is getting lower. So, temperature, so P v by T is constant. So, pressure is same, volume getting lower means temperature also has to be lower, because P v is proportional to T, right. P v is proportional to T. See, so pressure constant, so volume gets lower, temperature gets lower. Anyway, so now we know that. So, that this is a negative quantity basically. Okay, this is the heat that is going out. So, this is nothing but Q out, and 2 to 3 will be a Q in step, and this is a constant volume. So, it will be T 3 minus T 2. So, this is our in step, which is greater than 0, and 3 to 1 step is 0, it is an adiabatic process. So, what is the efficiency? Total heat change, which is Q 1 2 plus Q 2 3, and what is our input? Our input is Q 2 3. So, that we have to understand what is input and what is output, otherwise we will not be able to put it in the efficiency calculation. Heat input will go to the denominator, which means it is 1 plus Q 1 2 by Q 2 3. It is not minus, because by the minus itself, minus is there in the value itself in Q 1 2. So, therefore, it is just a plus, just to reiterate my earlier point. So, it is 1 plus. Now, Q 1 2 is this one C p T 2 minus T 1, and this is C v T 3 minus T 2. I will write in such a way that T2 comes one side. So, 1 minus Cp by Cv is gamma, and I took a minus, so that I can write T1 minus T2 and T3 minus T2. Now, let us take T2 common from numerator and denominator, giving me T1 by T2 minus 1, T3 by T2 minus 1. Now, what is T1 by T2, that we have to figure out. So, T1 and 2 are related by constant pressure process. So, let us just use the formula as P1 V1 by T1 is equal to P2 V2 by T2. Now, P1 and P2 are same. So, therefore, T1 by T2 is V1 by V2. So, we can write V1 by V2 here, and let us check between 3 and 2. So, 3 and 2 are related by constant volume process. Yes, 3 and 2 are related by constant volume process. So, we can write as P2 V2 by T2 is P3 V3 by T3. Since volume is same, V2 V3 is same. So, T3 by T2 will be P3 by P2, which means I can write 1 minus gamma T1 by T2 is V1 by V2. So, V1 by V2 minus 1, and T3 by T2 is P3 by P2 minus 1. So, this is our answer, right. So, it is pretty simple, the efficiency calculation is not, if you do this way, just to calculate the Q. If you want to calculate the work done and all, it will be very big. Just calculate the overall change in Q, and then essentially this formula is always correct. Okay, it is always correct only when you have one input and one output. If you have two input, then both the inputs will go in the denominator, right, and the numerator will have everything. So, that is why you have to be careful. It is better to have total heat divided by heat input, that is the definition, and that is we should stick to. Now, this is a conceptual problem that says that show that two adiabatic paths can never cross. Now, how do you think about that? So, let us say I have a PV diagram and I have an isothermal path. Isothermal is not drawn that way, but okay, let me just draw it once more. Let us have an isothermal path and I have two adiabatic path connecting. So, this is adiabatic, and this is isothermal. Let us say it is possible. What will happen? Can you tell me what will happen? If this is the case, let us calculate the efficiency. Eta is, we know that Q tot by Q in, right. What is Q in? So, Q cannot be in through any of this adiabatic process. So, this is the Q in, right. Let us say this is some value Q, and what is Q tot? Because Q tot, total Q is only that Q, because there is no other place, which is 1, which is not possible. So, if two adiabatic paths would cross, then you can always join them by an isothermal path, and that would violate second law of thermodynamics. Therefore, two adiabatic paths cannot cross. For ideal gas, you can obviously show that, because this, if two adiabatic crosses, then these two will have some relation with T and V, and these two also will have some relation with T and V, and those both the relations cannot be satisfied because the temperature is same here. That is another problem, because let us say this volume is V. So, this V and T has some relation, and this, because the volume is different here. So, temperature will be different here compared to here. You are getting my point? So, when you have this relation between this and this, since the volume is same between this step and this step, temperature will be different here, because the volume is changing differently compared to this point. So, this temperature and this temperature will be different, and therefore, but it is not possible because we are joining them by isothermal path. So, that is another way of thinking, but anyway. So, this is sufficient enough to show that if they cross, you can always join them by an isothermal path, and then it will violate the second law of thermodynamics. So, that is why two adiabats can never cross, and you can think upon the TS diagram also. So, two adiabats, if they have the different temperature in TS diagram, they cannot meet. So, this is T, this is S, this temperature is increasing here. Okay. So, this is between an adiabatic path. So, if another adiabat path is there which has a different temperature and different entropy, then they can never meet. It has to have same entropy, right, otherwise they cannot meet. That is why they cannot cross, because if you cross at some point, they will have to have same entropy and same temperature, because this is a state function, both entropy and temperature, right. At this point they have the same value, but it can never have same value unless it is the same path. If you start from here, it will follow the same path. See, that is another way of thinking it.